All right, let's just jump right in. What if I told you that one of the most basic, fundamental things you believe about reality, that a baseball follows one single clean arc when you throw it, is just flat out wrong? We're going to be digging into what might just be the most convincing illusion that nature has ever cooked up. It's a misunderstanding of how things work that even the smartest physicist had for centuries.
And look, this isn't just my take on it. This is a direct quote, a straight up admission from a physicist who's dedicated his life to this stuff. It's such a powerful way to start because it cuts right to the chase. The simple, predictable world we think we see, yeah, that's not the whole story. It's not even close. So that brings us to the big kind of mind-bending question for today. Just forget for a second about a single line from point A to point B. What if, down at the quantum level, a particle, an electron, a photon, you name it, actually tries out every single path you could possibly imagine to get there, and it does it all at the same time? It sounds completely bonkers, I know, but just stick with me. Let's see where this idea leads. To even begin to wrap our heads around this, we are not going to start with quantum mechanics. Nope, we're going to start with something way more relatable. A day at the beach, and a lifeguard who's got a serious problem to solve.
So, picture this. The lifeguard sees someone in trouble. What's the fastest way to get to them? Running in a straight line seems obvious, right? Shortest distance. But wait, running on sand is fast. Swimming is slow. So the actual fastest path isn't a straight line. It's running a little further down the beach to spend less time in the water. This is called the principle of least time, and it's exactly what light does when it bends going from air to water. But that leads to a really weird question. How does a beam of light know in advance which path is going to be the quickest?
For a long time, the classical answer was basically, well, it just does. It just follows the laws of physics. But that nice, comfy answer was about to get blown to bits by a massive crisis at the turn of the 20th century. A problem so bad, they called it the ultraviolet catastrophe.
Okay, but before we get to the catastrophe, we need to introduce the main character of our story, this really mysterious thing called action. For hundreds of years, physicists had noticed something strange. Nature is lazy. It's incredibly efficient. Planets, apples, you name it, they all seem to choose the path that costs the least amount of this action. It was like this cosmic currency that nature always tries to save, but nobody had a clue why. It was just a weird rule that always seemed to work.
And this graph shows you just how bad things got. Scientists were trying to predict the light coming off a hot object. Think of the glowing filament in an early light bulb. The real-world data, that's the second bar, showed the energy would peak at a certain color and then drop off. Simple enough. But the best theories they had, classical physics, predicted the first bar, that as you get to shorter wavelengths, like ultraviolet light, the energy would just shoot up to infinity. An infinite amount of energy coming out of a light bulb. I mean, that's just obviously spectacularly wrong. Physics was broken.
So, the physicist Max Planck was tearing his hair out over this. He tried everything. Finally, in what he himself called an act of desperation, he just made something up. He said, okay, what if energy isn't smooth and continuous, but comes in these little chunks, these little packets called quanta? And he said the energy of each packet is tied to its frequency by some new number, which he called h. He thought it was just a clunky mathematical trick. But when he ran the numbers, it matched the data perfectly. He'd solved the problem, but he had absolutely no idea why his crazy trick worked. Planck was actually really bothered by his own solution. He thought he just found a weird gimmick to get the right answer. What he didn't realize was that he'd accidentally stumbled upon one of the deepest secrets of the entire universe. And here it is. This is the big twist.
When Planck actually figured out the physical units for his new constant h, he got a shock. The units weren't for energy. They were joules multiplied by seconds, which are the units for action. He hadn't just found a minimum packet of energy. He had accidentally discovered the fundamental, indivisible Lego brick of action itself. Everything that happens in the universe has to happen in whole number chunks of h.
And this one idea, this h, became the golden thread that let scientists unravel the whole quantum world. First, in 1905, Einstein used it to prove light is made of particles. Then, Niels Bohr used it to explain why atoms don't just instantly collapse on themselves. He quantized their action. And then, finally, in 1924, Louis de Broglie tied it all together with an even wilder idea. If light waves can act like particles, maybe particles can act like waves.
And that was the key. De Broglie figured the only way an electron wave could possibly orbit a nucleus without crashing is if it formed a perfect, stable, standing wave. You know, like a guitar string. It has to have a whole number of its wavelengths fit perfectly around the circle. 1 wavelength, 2, 3, that's fine. But 2.5? Nope. It would interfere with itself and fall apart. For the first time, there was a real physical reason for why things are quantized. It wasn't just some math trick. It's because matter itself is a wave.
Okay, so particles are waves. This completely changed the game, and it opened the door for a brilliant young physicist named Richard Feynman to take this logic to its most extreme, mind-blowing conclusion.
This thought experiment is just beautiful. So you start with the famous double-slit experiment. We know the particle wave goes through both slits at once. Fine. Now, what if you add a third slit? Or a fourth? Or 10,000? The logic has to be the same, right? You have to account for the path through every single one of those slits. So, what happens when you add so many slits that the wall itself just disappears and you're left with empty space? The conclusion is inescapable. To get from point A to B, a particle has to take every possible path.
And when Feynman said every path, he really meant it, not just the sensible ones. His math forced him to include paths that wiggle and zigzag, paths that go backwards in time, paths that go faster than light, and yes, even paths that loop out to the far side of the moon and back before landing on your detector. All of them. They all have to be counted.
Okay, so this obviously raises a gigantic question. If a particle is taking all these absolutely insane paths, why in the world do we only ever see one? When I throw a baseball, it follows a perfect parabola. I don't see it take a detour around Jupiter. Why not? The answer, it turns out, is interference. The same way waves in a pond can cancel out or add up. Feynman imagined each path as having a tiny little spinning arrow. For almost all those crazy paths, the one to the moon, the one that wiggles, the arrows end up pointing in totally random directions. When you add them all up, they just cancel each other out. Poof, gone. That's destructive interference. But for the paths that are clustered right around that old-fashioned path of least action, something amazing happens. Their little arrows all end up pointing in almost the exact same direction. So they add up, they reinforce each other, and through constructive interference, they create the single path that we actually see. And that right there is the illusion. The single, solid, predictable path that we see in our everyday life, it's not the real thing. It's an emergent property. It's like the average of an infinite number of quantum possibilities all happening at once. The illusion is thinking there was only one path in the first place. Now, this could all sound like some fun, philosophical idea, a cool mathematical quirk, but it's not. This is one of the most rigorously tested ideas in science. It's been proven experimentally, and it forms the very foundation of all of modern physics.
And the proof is just mind-blowing. In one experiment, you shine a laser at a mirror, and you get a reflection in one specific spot, just where you'd expect. Then you cover that spot. But on another part of the mirror, a part that shouldn't be reflecting light to your detector, you put a special grating. This grating is designed to strategically block certain light paths, to stop them from canceling each other out. And what happens? A spot of light appears from the impossible location, proving, without a doubt, that the light was taking those other, weirder paths the entire time.
So what's the big takeaway here? Well, this principle of action is, well, everything. When you hear physicists talking about searching for a theory of everything, they're not just looking for new particles. What they're really hunting for is the one master formula for action, the Lagrangian of the universe, that when you plug it into Feynman's sum over all paths, it correctly spits out every single law of physics we've ever discovered. They're looking for the source code of the beautiful illusion we call reality.